In the last few classes, what we have been doing it is essentially showing that Lorentz transformations form a group, but the structure is much richer. As I have been saying that it is a very rich structure that it is just meaning these transformations have various other aspects of them and classification of them, which are very interesting essentially. One of the first ones to actually understand Lorentz group and its various classification properties is Wigner, and also the Indian mathematician essentially Harish Chandra has worked a lot on representation theory of Lorentz group and also Poincare group essentially. So the Poincare group and Lorentz group are foundations of on which quantum mechanics on relativity resides on or these are the foundations on which quantum field theory is built on, and that's the reason why I'm spending a lot of time on this Lorentz transformations essentially, and the aspect of Lorentz group. This is a very interesting thing for anybody who is interested in understanding Lorentz group and Lorentz meaning anything to do with relativistic quantum mechanics, relativistic quantum field theories. These are the foundations for it, and these are extremely important to understand. So as we started with Lorentz transform, or we recapped Lorentz transformations, which you already know in your special theory of relativity courses, and then we started looking at the condition that the metric should be invariant under these Lorentz transformations. And using this condition, essentially using this condition, we showed that Lorentz transformation form have all the satisfy all the postulates of Lorentz to form a group, like the closure property, the associativity property, the inverse, and the existence of an identity. But I said this condition itself is much broader, much richer essentially. Okay, so this also involves Lorentz transformations, which are a little bit more different. As like for example, these not just involve the ordinary Lorentz transformation which we believe to be, which are essentially boost. They also involve rotations, which are three of them, essentially three rotation SO3 group, which we have seen. So it has three generators. The boost have three generators, and they also have discrete properties, which we have seen just now essentially, which in the previous class essentially, which are essentially P, which stands for space inversion, and T, which stands for time inversion essentially. As we will call them, we'll associate them with parity operators and other time reversal operators later on, as when we start looking at the solutions of Dirac equation. But it is important that we should know that these are all incorporated within the Lorentz group. Okay, these are all incorporated within the Lorentz group, and that is the reason why they are reflected in the Dirac theory, or the theory which we will be seeing essentially. So so in such a way that the Lorentz group really forms the foundation on which the Dirac theory rests essentially, or all relativistic quantum mechanics and relativistic quantum field theories lie. Okay, this is the most important foundation essentially. So now coming, so what we have seen is that Lorentz transformations are boost plus rotations plus parity and time reversal, and just using this particular condition again and again, essentially that the metric should be invariant under Lorentz transformations, we classified Lorentz transformations as proper, improper, orthochronous, and non-orthochronous Lorentz transformations essentially. So the proper orthochronous transformations have determinant of the Lorentz transformation matrix as positive unity. This definition, so this is similar to, instead of like what we did for orthogonal or special unitary groups, except that now here we call it as a proper group, essentially proper transformation essentially. Okay, instead of calling it special. And lambda is equal to -1 is called improper. it's called improper. And the second other property is about the lambda 0 0 element, and this also comes from the same thing, but it's just focusing on the 0 0 component on of the metric. Okay, whether the first diagonal element of the metric, essentially the 1 1 0 0 or 1 1 component of the metric, is what are its on it. So the invariant contribution, the invariant conditions tells you that this element can be either greater than or equal to 1 or less than or equal to -1 essentially. Okay, these are the only two possibilities, and the case when it is greater than or equal to 1 is called orthochronous, and the case in which it is called less than or equal to -1 is called non-orthochronous. So the Lorentz transformations can be classified either in terms depending upon the sign of the determinant and also the sign of the lambda 0 0, can be classified either in terms of proper, improper, orthochronous or non-orthochronous condition Lorentz transformations. Now which of them form a group is the important point, because at the end of the day we want to look at the infinitesimal transformations of Lorentz of the Lorentz group of the Lorentz transformations, and look at generators and build the representation theory as we have been discussing in the previous classes essentially. And we have seen that all the proper transformations form a group, all the orthochronous transformations also form a group, and all the proper and orthochronous transformations form a group. While I have not proven this to you explicitly, but this can be just the way we derived the Lorentz group. Essentially the same conditions, you can go through them again and then you can see that all the proper transformations form a group, because the proper transformations are only this determinant greater than 1, otherwise rest of the conditions for forming of a group just follow through. Same thing with the orthochronous transformation, essentially there is no real constraint on it. And you can also have proper and orthochronous transformations really forming a group altogether. And of course then proper orthochronous and improper orthochronous also plus improper orthochronous also form a group. Now improper transformations are also important, like for example things like space inversion and time reversal are improper transformations because they have determinant is equal to -1, because one of them is -1. The space time translation is not, time inversion is -1 1 1 1 1, so it has a determinant -1, whereas space inversion is 1 -1 -1 -1, which has determinant is also again -1. So both these two are improper transformations. One of them is orthochronous because the space inversion is orthochronous, whereas the time inversion is non-orthochronous because it has lambda 0 0 -1 essentially. Okay, but boosts and rotations are orthochronous and proper essentially. So you can start off looking at infinitesimal transformations of Lorentz group, focusing on the proper and orthochronous part of it essentially. Okay, so that tells you that boost transformations, so they can be started off from unity, which is very nice, and that's the reason why we can connect it with a Lie group essentially. Okay, we can connect it with a Lie group. Good. So let's start with infinitesimal. So the infinitesimal Lorentz transformations, what we need is to just to say that we are going to start with a very small tiny Lorentz transformation, modifying around lambda mu nu is equal to g mu nu plus omega mu nu. Okay. Okay, omega mu are infinitesimal transformations. Okay, as we will see. And now we'll put it back into the condition that omega mu should also, we'll put now with this, now you put it back into the condition that the Lorentz transformation should leave you the metric invariant, the same condition which we have been using it essentially significantly over the time essentially. So this certain condition will give me lambda mu g mu nu sigma lambda nu rho is equal to g sigma rho. So this can be written in terms of lambda nu. I can you can put one of these things essentially into this essentially. So this gives me conditions of the sort essentially that it is lambda nu sigma lambda nu rho is equal to g sigma rho. Okay, so putting back this condition, the infinitesimal condition back into this, you will end up conditions like g sigma rho is equal to g sigma rho. I am not doing the entire thing here. Essentially you will end up having omega rho sigma plus omega sigma rho plus order omega square. So you will end up having a condition of this particular type. Okay, so you will end up having a condition. This tells you that g rho sigma should be equivalent to minus rho sigma rho. The matrix omega rho sigma should be anti-symmetric. So it should be anti-symmetric. Okay, so what it means that for infinitesimal transformations essentially, so this leads to, I am not, so this can be shown easily by substituting this condition here, essentially this condition into this. Okay, so rho and sigma can go from 0 to 3, so that is 4 entries essentially. So you will have 4 into 3 by 2, so n into n minus 1 by 2, that is equal to 6 entries, antisymmetric matrix which is 6 entries. So this will be of the form rho sigma or omega. Okay, let me just omega without writing the entries would be something like this. 0 0 1 omega 0 2 omega 0 3. Okay, 1 2 omega 1 3 omega 2 3 0. Oh, sorry, minus omega 0 1 0 minus omega 0 2 minus omega 1 2 0. It's a completely antisymmetric matrix. This is not unexpected. We have seen this earlier essentially that minus omega 0 3. I am doing everything a little bit explicitly because we need to get the feel essentially. Now because it is an antisymmetric matrix, it's the same elements repeating here, so the number of independent entries is 4 into for 4-dimensional matrix. So the number of for n-dimensional matrix, number of antisymmetric matrix is this. So that is 6. So this, which anyway you can calculate, just count it anyway. You don't have to redo it essentially. Good. Now what we do is actually we, corresponding to each parameter, we introduced a uh, introduce a generator sort of thing. Okay, we can introduce further antisymmetric matrices. I'll just to conveniently write it down. So this matrix omega, this you will see, you'll appreciate it in a second. Essentially why I am doing this is equal to omega is equal to omega 0 1 times, okay, 0 1 minus 1 0 0 0 0 0 0 0 0 0 0 0 0 plus omega 0 2. Now you can immediately recognize what I am doing. So you can immediately recognize what I am doing because this is what we did for rotation matrices and everything else essentially. So this is nothing but your generators. Okay, I'm just re-expressing this in terms of generators. Okay, instead of taking, otherwise I can define it in terms of derivative of the Lorentz transformation and everything. But this is the same thing. This is the same thing I am doing, but this is important to set the notation. So for example, okay, now the reason I am doing this, because then you will start recognizing a few things which are interesting. I hope I'm putting everything correctly essentially. uh, 1 2 plus, let me write it down, 1 3 uh, 0 2 2 3. Yeah, I had to write 2 3. Okay, so with this you can reconstruct your omega matrix, your infinitesimal rotation essentially, infinitesimal rotation. These matrices are called M matrices, M mu nu. These matrices are called M matrices. Okay, these are their generators essentially, 4 by 4 M mu nu. These are your M matrices. Okay, so this is your M01, M02, M03, M12, M13, M23 essentially, M12, M23 essentially. So these are 4 by 4 M matrices. So, but you can express very nicely M's into very nice form essentially. Okay, very nice form. Okay, first thing is you can write M mu nu, every element of M mu nu, or let's say M0I alpha beta matrix, essential alpha beta is equal to G mu alpha G nu beta minus G mu beta G nu alpha. So it's some sort of an antisymmetric combination of the metric tensor, essentially G mu nu G nu nu. Not sorry. Antisymmetric combination of product of metric matrices, essentially. Okay, taking them to be some sort of vectors, and other thing is, of course, they are antisymmetric. Mu nu alpha beta is equal to M nu mu alpha beta. So these are the two properties which we have. Okay, these are the two properties, and the generic alpha beta can be written as G alpha beta. Generic Lorentz transformation can be written in terms of mu nu M mu nu alpha beta. So this is the important thing that we have derived, that a generic Lorentz transformation is a deformation of the matrix. Okay, it's a deformation of this of the unit matrix with this particular thing, essentially, in terms of the first generators, what we have seen, essentially. So this is written in a very nice format most of the time, which we nicely write down, essentially. Okay, this is written in terms of, so most textbooks use lambda. Oh God, lambda is equal to, oh, why I'm doing this, lambda E, okay, lambda is equal to I is equal to half omega mu nu M mu nu. Okay, this is the definition of Lorentz transformation, infinitesimal Lorentz transformation. We will, oh sorry, this should be a plus. This is the definition of an infinitesimal Lorentz transformation. Now this is good, but with this I want to isolate boost and rotations, essentially. I want to isolate boost and rotations because that makes my life easier. Okay, I want to isolate boost and rotations. Okay, so so how do I do that? I identify, if you see the generators, essentially, if you see the generators, so there are generators which are 0I generators. So there are generators which are 0I. So if you take this as the space-time indices, essentially, okay, they are generators which are 0I, and there are the generators which are just ij. They are there are generators which are just which are just ij. So that means they are in the lower part, essentially, only on the space part, essentially. So I want to separate these two out. Okay, I want to separate these two out. So one I'll call it as a generators of boost, and other I call it as generators of rotations. So with this is essentially the starting point, essentially, of understanding of the Lorentz group, essentially, of the understanding of the representations. So let me introduce K M0I and J, or sometimes J or L is equal to mjk. Okay. So m0I are okay. What I did was essentially uh, so the this is m contains two indices 0 mu nu. Okay, 0I part of the m's I call them as k, and jk part are meaning 1, 2, 2, 3, that part of the m's I call them as j. So these corresponds to boost, these corresponds to rotations. So remember, we are looking at proper orthochronous rotations of the Lorentz group essentially. Okay, so we call them we have essentially um, um, uh, yeah, we can always deform them from unity. So we start with infinitesimal Lorentz transformations. So we started with infinitesimal Lorentz transformations, and we noticed that this number of parameters end up being 6 because these are antisymmetric combinations which can leave the metric invariant. These 6 transformations, these 6 parameters can be expressed, can be associated with the most general transformation is this particular fashion. So, but they can be associated with 6 generators, and we notice that the 6 generators have some difference essentially. Some of 3 of them come with they are essentially corresponds to boost, which are the 0I components of the Lorentz transformations, and 3 of them are just I and j part of the Lorentz transformations. So, or the space part of the Lorentz transformation, which gives you the rotations essentially. So now what we did was while we wrote down the most general form of the Lorentz transformations, so what we did was we also separated the uh, generators of boost and rotations into this particular fashion essentially. Now we can write down very interestingly essentially that now remember, now you have to be careful here essentially. We have to be careful here that K and J are 4 by 4 matrices. Not 3 by 3 matrices. Okay, they are not 3 by 3 or 2 by 2 matrices, they are 4 by 4 matrices. They are exactly like Lorentz transformations because we are looking at so they are exactly like Lorentz transformations. They are exactly like 4 by 4 matrices. So what we can do, we can express them the same matrices into uh, uh, in such a way that we remove the minus signs essentially. So the basic idea is that we want to say for example in the M0I we have we can define M0I is essentially, so we can define one of the indices to go up. So if we define one of the indices to go up essentially, so we can make them completely this will make our life easier, slightly different. So what we do is Ki alpha j, we call it as k cap, k same ki. Okay, let me alpha j. So one of the indices is moved up essentially. Okay, ki, and then we will do the same thing with li alpha beta becomes li. Essentially we just moved up the one of the indices, we have just moved it up one of the indices. Now this makes our life slightly easier because we can get rid of the minus signs essentially. Okay, so then we can make some identifications, we can really write in terms of some identifications. So what we, okay, um, um, Okay. Okay. So then let me write it down. Okay. Let me write it down. So ki1 would now be equivalent to 0, 1, 0, 0, 1, 0, 0. Without the minus sign, it's nothing but it's the same thing. K2 would be 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. K3 is equal to 0, 0, 0, 1, 0, 0, 1, 0, 0. Okay. And J or L, I don't know what I introduced. I introduced as L, L. No, okay, this should be L. L. Okay. L will still have the minus signs essentially. Okay. L still have the minus signs, but reversed. L1 will be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 1, 0, 0, 1, 0. L2 will have the minus signs 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, minus 1, 0, 0. L3 is equal to 0, 0, 0, 0, 0, 0, minus 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. Now the reason why we do this is now that you can see these L matrices and I matrices satisfy some simple relations. Okay, they satisfy some simple commutation relations. What you can see is that K I J I on the top, J on the left is equal to 0. K I 0 mu is equal to K I mu 0 is equal to G I mu. Mu is equal to 0, 1, 2, 3. Okay. I J K is equal to 1, 2, 3. Okay. The interesting thing is that Li Jk is minus epsilon Ijk. Lijk is minus epsilon Ijk, which is completely antisymmetric tensor. Okay, with this with the definition that Ijk is even permutation. Minus 1 for odd permutation. So with this observation, what I can do, I can write down the following commutation relations which we will start discussing is equal to minus epsilon Ijk Lk Li Lj is equal to epsilon Ijk Lk Li Kj is equal to epsilon Ijk Kk. These are the most important commutation relations. This is for rotations. They form a group on their own. These are boost, K's are boost. The commutation of boost is a rotation, and a boost and a commutation of a boost and a rotation is a boost. The computation of a boost and a rotation is a boost. Okay, so I'll stop here because we have reached a um, significant understanding of our Lorentz group essentially. So what we have seen is that the Lorentz group can be represented in terms of 6 parameters. A proper orthochronous Lorentz group can be represented in terms of 6 parameters, and each of these 6 parameters has generators, and the algebra is closed. We are just derived the algebra. The algebra can be written in terms of this M matrices, but the M matrices algebra, maybe I'll write it down later on. Essentially it's not very intuitive, meaning it's not very useful for us. Essentially, instead of the um, um, M generator algebra, the full M generator algebra, what we did was we separated it out as boost and rotation, which is the one which is useful for us essentially. And we saw that they form an algebra on their own. Essentially, they form, each of them form the rotations form an algebra of their own, and the boost form an algebra which gives you that it is connected with the rotation. They don't form an independent algebra. It is connected with the rotations essentially, whereas the rotation and boost also have an algebra associated with the boost essentially. So this is the main takeaway of the Lorentz group. So we will continuing understanding of the Lorentz group in the next coming classes, and we are reaching a very good stage of understanding the Lorentz group. Okay, I'll stop here, and then in the next class we will continue with the Lorentz group and its representations. Thank you very much.